Hello everybody, this is our video solution to problem 1 from quiz 14, spring 2023, Math 302 at Cal State Fullerton. In this problem, we are going to be trying to identify whether given sets, along with a binary operation, are groups. So let's jump right into it. The first problem, we're given the set of integers along with the binary operation multiplication, right? You multiply two integers, you again get an integer. Well, do we have a group? First, yeah, we know that multiplication of integers is associative. There's an identity element, right? The number 1, when you multiply by 1, you don't change your input. What about inverses? And there's where we get a problem. For example, the number 2 has no multiplicative inverse in Z. We know that the multiplicative inverse of 2 would be a half, which is not an integer. So this implies that the integers along with multiplication are not a group. All right, second one, now we're going to be looking not at all integers, but just at the non-negative ones. And our binary operation is supposed to be subtraction. Ooh, but even what I just said doesn't make sense. Our binary operation. That would mean that if I subtract any two non-negative integers, I would get another non-negative integer. But that's definitely not true. 3 minus 5 is equal to negative 2, which is not a non-negative integer. This implies that minus is not even a binary operation on z greater than or equal to 0. And consequently, z greater than or equal to 0 along with subtraction is not a group. Okay, that's kind of a trick one, right? Problem even suggests that it is a binary operation. All right, what about the third one? The set of rotational and reflective symmetries of a rectangle with composition. Okay, so I'm allowed to take a rectangle and rotate it, but only so that it's a symmetry, right? So for example, if I tried rotating this 90 degrees counterclockwise, I'd end up with a vertical rectangle. This would not be a symmetry. So I'm not going to be able to rotate by 90 degrees, but I could rotate by a full 180 degrees. So if instead of doing a 90-degree rotation, I rotate 180 degrees, I'll end up with another version of this rectangle. Looks the same, right? Except it's been rotated. So like if this was 1, 2, 3, 4, I rotate 180 degrees, and now my vertices, right, will have rotated. Of course, I could rotate again by 180 degrees, and that would just get me back to my original rectangle. And obviously, if I rotated backward, right, so clockwise by 180 degrees, it would give me the exact same rectangle here. All right, so I get that rotation. And what about reflections? Well, there's things like I could reflect across this vertical line or across this horizontal line. That would work. What if I tried going along one of these diagonals? Well, if I go along a diagonal, then I'm going to end up, again, getting one of these strange, it's going to look like a rotated rectangle. So let's see, we could maybe do some labeling now, right? So here's where I do the rotation by 180 degrees. Maybe I'll call that symmetry R. If I'm going to do this vertical one, let me call that S. And if I'm going to do this horizontal reflection, I'll call that T. So when I apply S, let's see, I'm doing the vertical one. The 1 and the 4 will swap. The 2 and the 3 will swap. If I instead applied the T, the 1 and the 2 would swap, and then the 3 and the 4 would swap. Okay, but I notice here, if I apply the S and then I rotate, this 1 ends up on the opposite corner, this 4 ends up on the opposite corner, this 3 the opposite corner, the 2 the opposite corner. That's actually the same as T. So I don't really need all of these letters. I actually get that T is equal to what happens if I reflect vertically and then I rotate. So in total, what do I actually get? So I would get the identity. We'll just label that with E. I have a rotation. I have this vertical reflection. And then I have here, of course, the reflection followed by the rotation. Now we might say, well, what if I go the other way around? So what if I rotate first, which is what we have here, and then I reflect vertically? So if I reflect vertically, then the 2 and the 3 swap, the 4 and the 1 swap, and actually I get t again. So I just write here that this is equal to the same thing. And we notice if I rotate twice, I get the identity. If I reflect twice, I get the identity. So in fact, this is everything I can get. It is definitely going to be associative because it's just function composition. We have an identity, and it's closed under products, and we have inverses because, right, R and S are their own inverses. And of course, if I do RS times RS, well, we know this is now the same thing as RSSR. SS is E, so this is RR, which is also E. So everything is its own inverse. So in fact, this is a group. So this is a group. Okay, and of course, more generally, when you look at the set of symmetries of a geometric object, you will get a group. In this case, a group of cardinality 4. This lives inside of what we call D8. That was the rotational and reflective symmetries of a square. Okay, of course, a rectangle, more general class. Unsurprisingly, you get fewer symmetries unless you happen to know that the rectangle is a square. All right, let's look at the last one, the set of 2 by 2 matrices with determinant 1 under multiplication. So first, if you multiply two 2 by 2 matrices with determinant 1, so let's say we have two 2 by 2 matrices. 2 by 2 matrices, and we didn't specify, but maybe we'll say over the real numbers. And if I assume that the determinant of both of these is 1, then the determinant of their product, right? Why the product? Well, because we said under multiplication. We know the determinant is a multiplicative map. So this is just equal to 1 times 1, which is 1. So again, AB is going to be a 2 by 2 matrix with determinant 1. Okay, cool. So we have closure here, right? We really do get a binary operation. This is matrix multiplication. We already know that's associative. Do we have an identity? Well, there is an identity matrix, and the determinant of the identity matrix, which is just 1, 0, 0, 1, is 1. It's just the product of the diagonals when you have a diagonal matrix. So that means the identity is in this set of matrices with determinant 1. What about inverses? Well, the inverse has determinant equal to 1 over the determinant of the matrix. But in this case, the determinant of A is 1. And so, once again, the determinant of the inverse will also have 1. And so that tells you that A inverse is a 2 by 2 matrix with determinant 1. Okay, and of course we know that A is invertible if it has determinant 1, because any matrix with unit determinant, right, must have an inverse. All right. By the way, just in case you're looking this up, there is a notation for this group of matrices. They usually call this SL2R. The S stands for special, the L for linear. So this is the special linear group 2 by 2 matrices over the reals. The SL, this just means 2 by 2 matrices with determinant 1. And this is a group. And there we go. All right, we will see you all next time.